Hello, welcome to another class of CS867 QIC890, and this week we'll be covering the gamma 2 norm and the approximate gamma 2 norm. So this week we are back to studying communication complexity. So just recall that in communication complexity, we're dealing with functions that take in two inputs. So we have a function f that will generally look like this. So this is going to be the functions we're studying instead of functions that take in n-bit strings. And we're going to have two players, Alice and Bob, and they will exchange bits. So Alice gets an input x from the set x, and Bob gets an input y from the set y, and they exchange bits until they know the answer, the output of the function f of xy. So they cooperate to compute f of xy, and the resource is the number of bits that they have to exchange. So we discussed this in an earlier week. So this week we are going to talk about a measure called the gamma 2 norm and approximate gamma 2 norm and its relation to approximate logrank. And this measure is basically like a communication complexity version of polynomial degree, of approximate degree for a Boolean function. So for a Boolean function, we had this polynomial method. We were able to show that q epsilon of f for a Boolean function, little f, is at least a half of this approximate degree with our epsilon of f. And then lower bounding this approximate degree is a way to lower bound quantum query complexity. And this was called the polynomial method. So that's in query complexity. In communication complexity, well, we'll put a little CC to indicate that this is a communication complexity measure. We can talk about the quantum communication complexity of the function f. And there's actually two versions of this. There's the shared entanglement version and the non-shared entanglement version, which we've discussed in the week on communication complexity. So there's two slightly different versions, and we want to lower bound this by a measure that depends on f, which is going to sort of be analogous to approximate degree. And so one thing to note is that, before we do find an analog for approximate degree, it makes sense to start with an analog of exact degree. So we can look at, what is the exact degree for a Boolean function. This is the degree of a function. And so we can ask, okay, what if we want a degree-like measure for a communication function f? And so it turns out that the measure logrank, the log of the rank of f, is a good proxy, and it serves as a good analog of the exact degree of a query complexity function. Okay, so let's just review what logrank is. So remember that we can represent f as a matrix where the rows are indexed by the set x and the columns are indexed by the set y. And at position little x comma little y, at this cell here, that's at row x and column y, we will have 0 if f of x, y equals 0, and otherwise we will have 1. So we will have these cells that have 0 or 1 in them. And so we will fill this matrix, and this matrix will define the communication function f. So communication functions correspond to these matrices. We can also represent these matrices. So we can either use zeros and ones for the two sort of output symbols for the function, or we can use 1 and -1. And we've seen this in query complexity when we dealt with degree of functions. Then we've seen that that often, we can switch back and forth from the 0-1 world and the -1-1 world, and it doesn't make a lot of difference, but sometimes one language is more convenient than the other. So here we can also do the same thing, and we can write f as a sign matrix where we will identify x with a matrix, f with a matrix. So f at position xy of the matrix is -1 to the power of f of xy. So we could represent it like this to kind of switch from this 0-1 values of fxy to -1-1 values in this way if we want. So then we'll have a sign matrix, a matrix with ones and -1s. So for either one of these matrices, we could look at the rank of the matrix. Okay, so this is just a thing you can do with any matrix, just the regular rank that you're used to from linear algebra. And the rank of the sign matrix version or the 0-1 version will only differ by +1, I believe, because you can sort of convert between, if I have a sign matrix, like if I have a matrix that goes 1, -1, -1, 1, and I want to convert it into a matrix that looks like, for example, 0, 1, 1, 0. For example, so here I converted ones to zeros and -1s to ones. If I want to do this conversion, I can just, do something like j minus f. So if f was this thing, then I can do j minus f over 2. So a half of j minus f, and that will convert one way. And similar simple linear transformations like this. So here, sorry, I should mention j here. I'm going to use j to denote the all ones matrix. That was always going to be the notation. So j is always going to be the all ones matrix. So here I can do this conversion in this direction by doing a half times j minus f. And in general, just any conversion, flipping the zeros and ones with each other, or changing 0, 1 to -1, 1 in any way can always be done by these simple linear transformations where you just add or subtract j and the matrix that you start with and multiply by some small constant or something like that. So just a simple linear transformation. And then, when you take the rank of such a thing, if you take the rank of this, then the constant factor of a half doesn't change the rank at all. And then we know that this is going to just be adding two matrices or subtracting them. Well, the rank is subadditive, so it's most it's most the rank of j plus the rank of f. And the rank of j is the all one matrix, so that's 1. So this is equal to 1 plus rank of f. So any of these transformations only changes the rank by up to a +1, where the +1 comes from the fact that j has rank 1. So the rank of a matrix is well defined up to a +1, depending on which on how you represent the output alphabet. Okay, so ignoring that +1, the rank is invariant to which alphabet symbols you're going to use for the output alphabet. And then so we can take the rank of a communication matrix F, and we can take the log of the result, and we get a measure called logrank. And we've argued that, we've argued in the communication class, in the communication week when we did communication complexity, that the deterministic communication complexity of F is at least the log of the rank of F. Okay, so so this is kind of gives us a reason to care about this, and the reason is that a communication protocol is going to split our matrix into these monochromatic rectangles that are all zeros or all ones, and if the protocol goes for t rounds, then it can split the matrix into 2 to the t different rectangles. And if the protocol correctly computes the function, then these rectangles must be monochromatic, which means that that f can be written as a sum of 2 to the t rectangles, each of which has rank 1, and so its rank is at most 2 to the t, 2 to the communication complexity. So we get this inequality here. Okay, so that's the exact rank. The reason it's sort of analogous to exact degree is because, well, okay, maybe this is not too easy to argue, but sort of very roughly the intuition is that if we want to talk about the degree of a Boolean function, we want to kind of write the function f of x as, a polynomial. So for example, maybe it's x1 minus x2 plus x1, x2 minus 3, x1, x3 plus whatever. So it's a polynomial that uses the variables of the input string x. And we care about the largest monomial, the monomial that uses the most variables. So if we have here x1, x2, x3, and that's the largest one, then we say that the degree is 3 for the function f. Now in communication complexity, there's no good way to measure the size of a monomial. So here, the query complexity, the size of a monomial is kind of how many bits do you look at once. But in communication complexity, there's no bits of the input to look at. So instead of counting size of monomials, like how many bits did you look at, in communication complexity, to kind of argue about lower bounds, we usually look at effectively how many different monomials you used, for example. So this is a related notion in that a polynomial of degree d will use at most n choose 0 plus n choose 1 plus up to n choose d, which is around n to the d different monomials. So a polynomial of degree d will only use n to the d or so different monomials. And so if we take the log of number of monomials used in the polynomial for f, okay, so if we take our polynomial, instead of measuring its degree, we measure the log of the number of monomials used, then the log of the number of monomials is going to be roughly d times log n. Now, of course, it could be less. It could be only one monomial, even though it's large. Okay, but so fine. So it's not exactly the same notion, but it's a very related measure, the log of number of monomials. And so it turns out that this kind of log of number of monomials measure is the right way to try to generalize to communication complexity. And instead of monomials in communication complexity, we'll use rectangles. Why? Because, well, monomials kind of, they sort of naturally correspond to rectangles in a sense that if you are partway through a query algorithm, then imagine you have a deterministic query algorithm and you ran it for t steps. So now you're partway through the algorithms. How might you represent your partial knowledge of the input string? Well, the partial knowledge of the input string is represented by a partial assignment, like a sequence of zeros and ones that you've seen, okay, which is a similar concept to a monomial. It's like a partial assignment. So it's like the variables we've already seen. Whereas in communication complexity, if you wanted to represent a partial knowledge you have about the input halfway through the protocol, then you should pretend that you're the referee and you stand in between Alice and Bob and only see what they've told you. And so what do you know halfway through the protocol? Well, if this is the communication matrix, then Alice sends you a bit. Then she kind of tells you whether she's in the top half of the matrix or the bottom half. Then Bob tells you a bit, which splits it further into these different sections, as we've discussed in the week on communication complexity. And so your partial knowledge is that as a referee, after they've sent each other a couple of bits, is basically which rectangle the input XY is in. So the partial knowledge after Alice sends Bob this bit and Bob returns a bit that's either this one or this one. So is that the input XY lies within, it's over here. It lies within this rectangle. Okay, as if you were standing in between them and listening to their messages. So partial knowledge in a communication protocol is sort of represented by a rectangle. Okay, so it's so there's a sense in which rectangles sort of correspond to partial assignments. And partial assignments are sort of like monomials. So, if we want to say, I want to represent my function using few monomials as a sum of only, say, n to the d monomials, that's a little bit similar to saying that I want to represent my function as a linear combination of few rectangles. But now we're really talking about a similar concept to rank, because rank is just asking to represent your matrix as a linear combination of few rank 1 matrices. Okay, and rank 1 matrices are well, they're not exactly rectangles, but they're very similar concept to rectangles. So with a little bit of hand waving, log rank in communication complexity is very roughly equivalent to log of number of monomials in a polynomial, which is very roughly, the degree. It doesn't have to be exactly the degree. You will at least be off by this log n factor, but you could be off by more in some special cases where you have few monomials, but still large degree. Okay, but kind of conceptually, these notions are kind of related. And so that's exact log rank. That this lower bounds deterministic protocols, and exact degree also lower bounds deterministic query complexity. So we want to talk about an approximate version, which will lower bound randomized and even quantum communication protocols. Okay, so this approximate version is going to be called approximate log rank. And so we define approximate log rank as follows. So, we have our original matrix. And, this is a communication matrix we want to compute. It's like, whatever. This is the communication matrix. And what we want to do is, instead of taking the log rank of f, we will take the minimum over matrices A that are roughly equal to f of the log rank of A. Or, I mean, we can pull the log up front, so we can, we can put the log up front. So we can define the approximate rank of f. We can define this to be the minimum over matrices that are similar to f, that are roughly equal to f, of the rank of the matrix. Okay, and what do I mean by similar to f? I mean close in the infinity norm. I mean at every entry, A has to be close to F, let's say within 1/3 of F. So basically, let's say a valid A here will be a matrix that is, let's say here it's 0, here instead of 1, it will be 0.9 instead of 1. Then instead of 0, it will be 0.1 here, 0.2 over here. Then I'll have a 0.1 for the 0 here, 0.8, 0.9, 1, 0.9, 0, 0.2, and 0.9. So I have this matrix, and at every entry, it's within 0.2 of the entry over here. And also all the entries are bounded between 0 and 1. So this matrix A is an approximation of the matrix F at every entry. Okay. And yet, by relaxing this, I might be able to get A to have lower rank than F. Okay. So the approximate rank of F, 2 error epsilon, will be the minimum over all matrices A that approximate F 2 error epsilon of the rank of that matrix A. Okay. So this is sort of like we allow the addition of noise to these Boolean values in F. And then we minimize the rank for that. Okay. And we're actually going to usually work with sign matrices. So we actually will take F to generally be, a +1 -1 thing. And then A will approximate that, but it's the same type of approximation. The notions of approximate rank in these two cases, you can again convert between one and the other just by adding and subtracting the all ones matrix and dividing by a constant. So it's only going to change the rank by even the approximate rank by at most 1. So the approximate rank is not sensitive to whether we use +1 -1 or 0 1. Okay, so that's the approximate rank. But then there's this issue that the approximate rank actually can't be computed quickly. So it's hard to even figure out, if I give you a matrix, what is the minimum rank I can get it to by adding noise to all the entries. That's actually a difficult problem. And I don't know if it's known to be NP hard, but in any case, it's not. So calculating the rank of a matrix is simple. Calculating the approximate rank of a matrix is actually very complicated, and I think it's known to be a hard problem to calculate it exactly, at least. So this measure we've introduced is actually not going to be very easy to use. It doesn't have great mathematical properties. It's not going to be very easy to directly argue that it lower bounds what we wanted to lower bound. So, well, one thing we should say in its favor, though, is that it does lower bound quantum communication complexity, but only without shared entanglement. So this is true. The following is true. The log of approximate rank. So this is true without shared entanglement. This means that the log of the approximate rank is sort of a useful measure, is sort of the measure we want for approximate degree, except for this annoying difference between the shared entanglement version of quantum communication complexity and the non-shared entanglement. And remember that we don't actually have a separation between the two. And yet, on paper, it seems like the shared entanglement version might be stronger as a model. So you might have a smaller quantum communication complexity for some function, even though we don't have a separation. So, one nice thing to do, it turns out, is to switch from this measure of approximate log rank, which lower bounds quantum communication and complexity without shared entanglement. We switch to a related measure that we'll define called the approximate gamma 2 norm. So here instead we'll have a log of approximate gamma 2 norm of F. So gamma 2 norm instead of rank. And then it will turn out that this lower bounds the quantum communication even with shared entanglement. So I put the star here to denote that with shared entanglement. So we have a kind of a better lower bound technique. Also, it will turn out that log of approximate gamma 2 norm is roughly equal to log rank of F. Okay, there's a bit of a loss there. Okay, so the loss depends a little bit on the epsilon, on the error level that you want to allow. So this approximate gamma 2 norm also takes in an error level epsilon somewhere. Okay, so so the loss here in when they're equal and when they're not depends on epsilon. And it also depends on the size of the matrix F. 1 second. Okay. So the loss here depends also on the size of F. So there's a bit of a loss in between the conversion of approximate gamma 2 norm and approximate log rank, but they're very similar measures. And so it's interesting to note that this measure is basically better in that it also lower bounds quantum communication complexity with shared entanglement. And additionally, the gamma 2, even the approximate gamma 2 norm of F is easy to compute. And it's mathematically nice. So it has a lot of nice properties. It can be written as a semi-definite program. We can take a dual of this thing. So it's kind of a good way, of viewing the approximate log rank. It's basically very similar with the log of the approximate gamma 2 norm. And so this is basically the measure we want to study, and we also kind of want to take the dual, as that will help us provide actual lower bounds. So what is the approximate gamma 2 norm? So the approximate gamma 2 norm, well, this is just going to be equal to the min over matrices A that approximate F to error epsilon of the gamma 2 norm of A. Okay, so that's not very helpful. It's the same definition as with rank for how we define approximate rank out of the exact rank. So here, that's how we define approximate gamma 2 norm out of the exact gamma 2 norm. So the question is, what is the exact gamma 2 norm? And the exact gamma 2 norm is kind of a relaxed or smaller version of rank that has nicer properties than rank. It's like a smooth version of rank. Rank is, of course, an integer valued function of a matrix. It tells you an integer for what the rank is of the matrix. Gamma 2 is it's a norm, so it's it varies with if you scale the matrix by a factor of 2, the gamma 2 norm will increase by a factor of 2. It's a norm, but other than the fact that it's a norm, it sort of behaves surprisingly similar to rank. So there's a list in the notes of a lot of different properties of the gamma 2 norm. But one thing to note is that the gamma 2 norm of a matrix is, well, it's at least the infinity norm of the matrix. This is the infinity norm of A is the largest entry, the absolute value of the largest entry. And it's at most the infinity norm of A times square root of the rank. Okay, so it's smaller than the rank. Now we're going to look at matrices that have values between -1 and 1. So for such matrices, the infinity norm is always going to just be at most 1. So for those matrices, this will actually look like this, like gamma 2 norm of the matrix A will be between 1 and square root rank. Okay, so this is smaller than rank. It's even smaller than square root rank. Of course, we'll take a log later, and once we take a log, then we get the log gamma 2 norm is smaller than half of log rank. Okay, So we'll eventually be interested in the log of this measure, and so the square root is not too much of a loss. It's not too scary. It's really just a factor of 2. Okay, but of course, gamma 2 norm can be smaller. It doesn't have to be equal to square root of rank. Okay, and gamma 2 norm. So well, again, so it's a norm. So gamma 2 of lambda times a, where if lambda is a scalar, is equal to the absolute value of lambda times gamma 2 norm of a, and also gamma 2 norm of a plus b, if these are two matrices, is at most gamma 2 norm of a plus gamma 2 norm of b. Okay, and finally gamma 2 norm of, if gamma 2 norm of a is 0, then this is equivalent to a being the all 0 matrix. Okay, so it's a norm. It has very many other very useful properties. For example, the gamma 2 norm of a tensor product of a and b is equal to gamma 2 norm of a times gamma 2 norm of b. Okay, the product. And gamma 2 norm of a Hadamard product, this is an entry-wise product of a and b, is at most gamma 2 norm of a times gamma 2 norm of b. And another useful property is that if C is a submatrix of A, then the gamma 2 norm of C is at most the gamma 2 norm of A. And it has various other kind of nice properties. Rearranging rows and columns of the matrix does not change the gamma 2 norm. Negating the matrix doesn't change gamma 2 norm. Various properties like that. The gamma 2 norm also, the gamma 2 norm of a matrix is also at most the largest singular value. This is the spectral norm of the matrix. So it's at most a spectral norm, and it's at least sort of the average singular value. So if it's at least what's called the trace norm, which is the sum of singular values divided by square root of n times m, where n and m are the dimensions of the matrix. Okay, so this is the geometric mean of the two dimensions of the matrix. So this is, the bottom here is roughly the dimension of the matrix. So here we have the gamma 2 norm is basically at least this is roughly the average singular value, and at most the maximum singular value. Okay, so this is roughly the size of the gamma 2 norm of the matrix. Okay, so how do you actually define this thing, though? So it has all of these convenient properties, but how do you define it? So the definition of the gamma 2 norm, there's actually two definitions that are non-trivially equivalent. So the gamma 2 norm of A, we can write it as the minimum over matrices B and C such that B times C equals A of the norm, the row norm of B and column norm of C, I think. So this is these are the maximum max 2 norm of a row of B, and then this is just going to be equal to the max 2 norm of a column of C. So max 2 norm of a column of C. Okay, so I hope I didn't flip the R and the C here. So you should check the notes for the actual version. So this is a factorization norm formulation. Here we wrote the norm of A, the gamma 2 norm, as the minimum over factorizations of A into a matrix product B times C of a norm of B times a norm of C. Okay, so this is a weird thing to do. But okay, that's one definition of the gamma 2 norm of A. There's another equivalent definition. The gamma 2 norm of A is equal to the maximum over matrices B that are not equal to 0 of the spectral norm of A Hadamard product B divided by the spectral norm of B. So I guess check the notes again to double check that I got it right. So this is a max formulation. So here there's sort of two dual versions of the gamma 2 norm. One is a minimization program that it gives you easy upper bounds in the gamma 2 norm by just displaying the matrices B and C. And one is as a maximization program and gives you easy lower bounds by just providing the matrix B. Okay, and here the norm here is a spectral norm, and the product is a Hadamard, like entry-wise product. Okay, so so this is the two strange definitions of gamma 2 norm. The second one you may look familiar from the definition of the negative weighted adversary bound that had something similar to this. So that had something called the filtered gamma 2 norm. Okay, anyway, so so this is the definition of gamma 2 norm. Another very nice property of the gamma 2 norm is that is something called growth index inequality. So again, I'll refer to the notes for a kind of formal version of this, but the growth index inequality relates the gamma 2 norm to this other norm that's sometimes called the nuclear norm, or the the growth index inequality converts the gamma 2 norm of the matrix. It says that up to constant factors, this is equal to this other norm. And this other norm is basically saying, okay, write A, decompose A into a linear combination of rank 1 sign matrices. So this is sort of like a linear combination of rectangles. And in fact, one version of growth index inequality that's in the notes just has A being decomposed into a linear combination of rectangles. Okay, so let's maybe it's easier to present it in terms of rectangles directly. So let's write A as a linear combination of rectangles. So we will write it as coefficient of a rectangle times a rectangle, and then a sum over all possible rectangles, where each rectangle R basically looks like this. It looks like a matrix where you have ones arranged in some rectangle, and then you have zeros everywhere else. So the whole rest of the matrix is zeros, and then there's some rectangle there that has all ones. And a rectangle can be any kind of set that's induced by a set of rows and a set of columns. So I mean, this is still considered a rectangle, just because we have a set of rows that are selected, these two rows, times a set of columns that are selected. Okay, so this would also be a rectangle. And so we are writing here A as a linear combination of rectangles. There's more than one way to do this. This is not a unique way to do it. Okay. Now, these are the coefficients of the linear combination. So for each decomposition of A, each time we write A as a linear combination of rectangles, we can ask how much coefficient did we use. So we can ask, what is the sum over R of the absolute value of CR? Okay. You know, and this new norm, or one version of it in the notes, asks to minimize this expression such that the sum of this linear combination of rectangles with these coefficients really is the matrix A. Okay, and so this is a norm of the matrix A. Okay, so you can do this. So we did this with rectangles just now. The official nuclear norm, as defined in the notes, actually does it with rank 1 sign matrices, but those are very similar to rectangles. So it's not too hard to convert back and forth and lose a constant factor between the two notions, either rank 1 sign matrices or rectangles. So officially the nuclear norm uses rank 1 sign matrices. But okay, but this it's easy to convert back and forth. Growth index inequality then says that this minimum, so this norm that we get here by taking this minimum, is within a constant factor of the gamma 2 norm. In fact, the constant factor is very small. The constant factor is called the growth index constant, the maximum value of the constant factor. It's something in order with kg. It's roughly 1.7, but we don't know the exact value. So it's less than a factor of 2 away from each other, the gamma 2 norm and this nuclear norm. And so the exact constant actually depends on whether we use rank 1 sign matrices, which is what growth index used, or rectangles, which loses another factor of 4. Okay, but that's fine. So so we have another characterization of the gamma 2 norm, which basically says that it's the sum of absolute values of coefficients that we need in order to write the matrix A as a linear combination of rectangles. Now, remembering that rectangles were roughly corresponding to monomials, this is like saying that instead of counting the number of monomials and taking a log, what we're going to do here is sum the coefficients, sum the absolute values of the coefficients. Okay, so we're going to sum the absolute value of the coefficients. Now, the two, whether we do rectangles or rank 1 sign matrices, is sort of going to be just the difference between whether we represent the polynomial in the +1 -1 basis or the 0 1 basis. And so that can change the coefficients. So with a lot of hand waving, this measure is a bit like taking the sum of absolute values of coefficients of a polynomial, and then it's a polynomial that only approximates the function, because we are going to want A to merely approximate F when we deal with the approximate gamma 2 norm. And then we take a log, and that resulting measure is a proxy for the approximate degree in query complexity, and the measure in communication complexity is, it's called, well, it's this is the log of gamma 2 norm, of approximate gamma 2 norm. And this is going to be roughly the communication analog of polynomial degree. And it lower bounds quantum communication complexity even with shared entanglement, which is kind of the key useful property of this thing. Again, the measure gamma 2 norm, it has a lot of useful properties. So it's often, it turns out to be feasible to work with it directly. But also we can work with this growth and decversion norm. We can work with the nuclear norm, or instead of working with the gamma 2 norm if we wanted. And of course, this would be an approximate version of it. So we could work with that as well. And in the notes, I took a dual of basically an approximate version of the rectangle version of this norm. So I took this called the mu norm, which is the rectangle version of the nuclear norm. And so you can define this thing, and I wrote a dual formulation of it to kind of show how you would prove a lower bound on this measure. And the dual formulation of it ended up looking surprisingly, well, perhaps surprisingly similar to the dual formulation of approximate degree that we saw in this course. So this is sort of more evidence that what we're dealing with here is basically a communication complexity version of approximate degree. And so this dual formulation can be used to lower bound the communication complexity of of functions, the quantum communication complexity. It's not that easy to use in practice. What's missing for us in communication complexity is a notion of symmetrization. So the symmetrization arguments sort of don't seem to generalize to communication complexity. The dual polynomial technique does. So the dual polynomial technique does have a communication complexity analog. So it's just a little hard to use in practice. One very nice application, though, is for a lifting theorem by Cherstov. So Cherstov in maybe 2005, I think, showed that if you take any so if you have any query function and you take a simple communication gadget G, like the 2-bit inner product function, let's call it IP2. This is a communication complexity function where Alice and Bob have 2 bits each. So it looks like this. So it's a simple communication function for inner product on 2 bits each. And then he showed that essentially that the log rank of F composed G is at least the approximate degree. It's an omega thing of the approximate degree of F. I'm hoping I'm not forgetting. I don't remember if he loses log factors or not. So this is called a lifting theorem, and it can convert any polynomial lower bound on the Boolean function F into communication lower bound and even an approximate log rank lower bound on F composed G. This is for a kind of a lifted function. Now you have a communication function F composed G, and many natural communication functions. So many natural functions you want, functions F, can actually be written as F composed G for correctly chosen G and F. And then you kind of try to apply Sherstow's lifting theorem. He called it the pattern matrix method. So you can try to apply it. This lifting theorem really does go through this essentially dual polynomial technique. And I believe that Sherstow does prove a log gamma 2 norm lower bound directly. Of course, log approximate rank and log approximate gamma 2 norm are related. The relationship depends on the size of the matrix. So the size of the function F, you lose a logarithmic factor there, and also depends on the error epsilon that you're dealing with. Okay, so in general, there's going to be a bunch of log losses and losses of some sort of small order terms. But you can lift any lower bound that you had in query complexity into a lower bound on a related communication function. And this is often a good way to get communication lower bounds for problems you care about. It's basically to show that, oh, this problem embeds a lifted function. This problem, as a special case of it, contains a lifted function. And to handle the listed function, we can use Sherstow's lifting theorem. You can even handle other gadgets, I believe. And often, you can convert from one gadget to another as well. So basically, you want to use various conversions to find a lifted function within the function you want to lower bound, and then apply Sherstow's lifting theorem, which he called the pattern matrix method. He doesn't call it a lifting theorem. That terminology is a bit more modern. Okay, so that's basically the gist of what I had to say about that. Just to talk about the gamma 2 norm is kind of has a lot of nice properties as a norm in itself. The approximate version of it, which once you take a log, corresponds to a communication version of approximate degree, the polynomial method, basically. And this is one of the main ways we have of lower bounding, showing the non-existence of quantum communication protocols, especially with shared entanglement. So it's a very useful lower bound technique there. Okay, so I will stop here and I will see you in class.